All right, one of our last topics that we're going to look at. We're going to look at functions of more than one variable. So the key here is we're going to have a couple of different variables going on. It's going to look a little bit confusing at first, but the more we work with it, the easier it'll be. We're mostly going to look at functions with two variables. We'll notice here that we've got z. This here is actually going to be an output variable. And then we've got this as a function f of x comma y, where normally we had f of x was equal to y, something like this. Now we've got z is equal to f of x comma y, where x and y are both independent variables here. These are both inputs. A key, though, is that if they're independent from each other, they're not going to be changing when the other one is changed. They're not dependent on each other. They're not leaning on each other. Their outcomes aren't going to be based on each other. But z is going to be the dependent variable that's based off of x and y. So again, we've got two inputs, one output. There's a really easy kind of analog example that we can look at. We can talk about cost functions. Normally we've been saying things like this. Maybe we have a company whose cost function is something like 1,000 plus 2x. Maybe we're looking at producing maybe flash drives. And so we've got $1,000 overhead, and it costs us $2 per flash drive. We can build a total cost from there. But what if our company also produces hard drives for computers? Maybe now we have a total cost where we still have $1,000 overhead, and it still costs us $2 per flash drive, but maybe it also costs us $7 per hard drive. Now we have a cost function that's based on both x and y. X and y are both going to be impacting our costs, but we'll notice that the number of hard drives doesn't impact what's happening with our flash drives, and the number of flash drives doesn't impact what's happening with our hard drives. X and y are independent of each other. They're not based on each other at all. So we'll follow these types of examples along, and we can kind of look at what happens with some of these. Let me close that parenthesis off. There we go. Here's some more examples that we've got. We could talk about an area function of some sort of a rectangle. It's going to be x times y, so it's based on two variables here. Sometimes we'll call those length and width or base and height. Here we could talk about this investment, and the balance is based on principal, rate, and time. Here we've got this continuously compounded interest, so it's PE to the RT. It's based on these three variables. We could fix P. We could say, all right, let's assume for all of these our principal is $10,000. And now our function is only based on rate and time, because we might have different interest rates for different lengths of time, and we'll have different balances along the way. So we can take one variable and just say, let's assume that it's always whatever number. And now it's not varying at all. It's not changing. It's a constant. But that's something we'll look at later. We could talk about the volume of a box, length, width, and height. It's what it's based on, and our volume is length times width times height. And then we've got these other functions. Again, the thing to notice is that these look like implicit differentiation examples, but x and y aren't based on each other. It's not that y is an output based on x as an input, or y is a function. Here, x and y are both inputs, and the function output is going to be whatever happens when we plug variables in here. Here we've got another function and another one. And maybe we'll look later at what these graphs actually look like to try and visualize these. When we're visualizing them, we're going to have three dimensions. We have an x-axis that normally is drawn like this, a y-axis that's normally drawn this way, and a z-axis that's normally vertical. So we'll have x there, y there, and z there. And if we want to look at the negative side of each of those, we could say there's the negative x-axis, the negative y-axis, and the negative z-axis. The easiest way that I can visualize this is by pretending I'm looking into a corner of a room where this here is the wall, or the floor, sorry, and then we've got one wall here and another wall here, and we're kind of looking down into the corner. And these corners here are the different axes that we have. When we draw points, they're going to be with different coordinates, so maybe we have something like an x value of 2 and a y value of 1 and a z value of 3. And now we're somewhere like right around here, maybe. And this point would be like 2, 1, 3. X value of 2, y value of 1, z value of 3. This is very difficult to visualize because really this is floating in space in front of this corner, but it's hard to tell when you're drawing it on a piece of paper. So we're not going to focus a lot on graphing these, but I will try and help us visualize them because that'll help with some concepts later on. Let's really just look at some evaluation stuff. This is pretty quick and easy, and you guys will get this without any problems. Here, if we're going to evaluate a function at a point, we need now two inputs, so x and y. And this is going to work exactly the way that you think. Here, if we want to evaluate this function, we'll plug in 2, we'll plug in -1, and we're just going to put them in place of those variables. So 3 times 2 times -1 minus 4 times 2 plus -1 minus 4. Our output now is -6 minus 8 minus 1 minus 4. And so now what do we have here? -6 minus 8 is -14, -15, and then minus 4 is now -19. So at an x value of 2 and a y value of -1, somewhere around here, if we go backwards on our y value, we end up really far down at -19 for our z value. So we've got a point, 2, -1, -19. So that's all we really have for evaluating things. You're just plugging stuff in. If we want, we can take a look at, let me pull up this GeoGebra applet that I've got. We can take a look at some graphs. So here's our axes. So we can see here that this red one is our x-axis, this green one is our y-axis, and this blue one is our z-axis. Let me just take this point, and I'm going to put it at 1, 0, 0. And I'll make it show up. And you can see here's our point right here. I can move it around so you can see where that point is. If we want to drag this point around, let me put it back into our kind of normal view. If you want to drag this point around, I might drag it into, I don't know, maybe right around here. So it's at like around 1.3 on our, maybe I'll bring it out this way. There we go. Now we're at 2, 2, 0. That's a nice easy one. This is kind of hard to tell exactly where it is, but if we move a little bit, we can see that we've got 2 on our x value, 2 for our y value, and our vertical component z is 0. See how it's laying flat right down the middle there? If we move this around, I can give it a little spin. It's a little easier to see where that point actually is floating. Now, obviously, this is very difficult to do when you're drawing graphs on your paper. And so we're not going to be sketching much of this. But we could include some other points. Here's a nice little point that's on our y-axis, and here's a point on the z-axis that we can see. What we can also do, if I get rid of this point, is graph some of these functions that we looked at. Here's the first one, that x minus 2 squared plus y minus 2 squared. This kind of looks like a parabola, but it's like a three-dimensional thing. It's like a cup here. You can kind of see inside of it. Again, difficult to draw because we have to do some shading and all that kind of stuff. Let me put in a point here. You can see this point right here. This is when x is equal to 0 and y is equal to 0. And if I just drag these x values along, now I'm going to move it along my red axis in the positive direction. You'll notice that the point moves along, and it's kind of on that little curve that you can see that looks like a parabola. So it's sliding around on the inside of this thing, and this is just moving along the x-axis, changing those red axis values. And I can do the same thing for the green one, and now you'll notice it moves in the other direction. It dips down into the middle of our kind of parabola cup type thing. And what you'll notice is that for each of these, when I change one of these variables, right now when I'm changing y, my point isn't moving along that x-axis very much. This is really easy to tell if we just grab this thing, make it stop, and we'll just look at our x-axis now. I'm going to try and visualize it looking right down the barrel of the y-axis. That's close enough. And now, when I change my y value, it moves up and down, but it doesn't look like it's moving left or right at all. You see that? See how our point is kind of stationary in terms of where it's moving left and right. And if I do this, now it's kind of looking like it's just running along a parabola, just like it normally would. But if I rearrange this and look down the barrel of the x-axis, and I can just see my y-axis here and my z-axis here, then when I change my x, we got the same thing. Because really what our point is doing is it's moving backwards and forwards right now. We just can't tell because we're looking at it straight on. So that's why we end up visualizing things this way. Let me make sure it doesn't roll around too much. There we go. And now when I move this point, I can kind of see it dragging along these axes. We've got a couple other cool surfaces that we can look at. This one's kind of cool. It's like we call this one like a saddle point in the middle. It kind of looks like a Pringles chip in that it curves off in kind of two different parabolas here. You can see underneath it looks like it's kind of curving downwards, and then off to the side, if we look at it, it's curving upwards. So if we pick some points on that, we can kind of drag them around and they roll around the surface of these. Again, as we move these points, they're not changing in the other direction. If I change the x variable, it's not changing in the y direction. And here's another interesting one that we can look at. This one's a little hard to see. We've got that same kind of thing, but you'll notice it's kind of got this steep drop-off point. It's still got these weird parabola type things where it looks like it's curving down here and up over here. And now when we drag our points around, they'll move around the outside of this surface. These are hard to visualize and kind of harder to play with, but what we're going to do is do a bit of calculus on these, just a small bit, where we're really going to make use of the fact that when we change one variable, the other variable doesn't change at all. And so these variables are independent of each other. When we talk about changing variables, we're talking about derivatives here. So that's what we're going to introduce next time. We'll talk about how to do some differentiation on these functions. But for now, get an idea for how these three-dimensional functions work. We're going to be evaluating functions and stuff like that, and it's all going to work out the same way that we used to think it would. All right, that's everything we've got here.